I'll be presenting the paper Preventing Network Bottlenecks, Accelerating Data Center Services with Hotspot Aware Placement for Compute and Storage. This paper tackles a very practical and important problem in large scale data centers. What happens when parts of your network becomes persistently overloaded and your traditional tools can't fix it? The authors not only characterize the problem in depth but also propose and deploy real solutions that they are running in production at Google today. We'll cover the background, the problem, the proposed solution, the evaluation results, and then a critical analysis of the work's strengths and limitations. Let's start with the core motivation. The ideal goal in any data center network is to give applications the illusion of an unconstrained network. You send traffic, it gets there fast and no bottlenecks. That's what network engineers aim for. But in practice, this illusion breaks down. Data centers have what the authors call hotspots, specifically top of rack switches whose uplinks run at persistently high utilization, which are above 75% for extended periods of times. Now we look at the diagram on the right. A typical data center has racks, each connected through a top of rack switch, which then connects upward through aggregation switches to the border DCNI. The top of rack switches is the first shared bottleneck between all the hosts in a rack and the rest of the network. The graph here makes a key observation. A small fraction of top of racks run consistently hot near 100% utilization, while the median TORs are lightly loaded. So this isn't a global network capacity problem. It's a localized, persistent overloaded problem. And here is the critical insight. When all the uplinks of a TOR are saturated, standard techniques like congestion control and load balancing simply cannot help. You can't spread traffic across multiple paths if the bottleneck is the single TOR itself. You can't pace traffic if the pipe is persistently full. The paper distributes the problem into three parts. First, a characterization study, which like it speaks about what causes hotspots, how frequent are they, how long do they last, and what production instance have they caused. Second, an impact analysis, specifically how much do TOR hotspots degrade storage and compute operation performance, like reads and writes. And third, they introduce a solution where they introduce two hotspot aware placement strategies, one for compute tasks and one for storage data. Here we speak about the root cause of hotspots. The authors argue is a demand supply imbalance at the rack level. On the demand side, different workloads have wildly varying network needs. The top CDF graph here shows that peak throughput per compute unit spans more than an order of magnitude. Some tasks are very network intensive, others barely use network at all. On the supply side, TOR uplink capacity per compute unit also varies significantly across racks by about 2 times across the fleet. This is largely due to incremental hardware upgrades over time. Newer machines get installed in existing racks, changing the ratio of compute capacity to network capacity. When you combine heterogeneous demand with heterogeneous supply and your scheduler doesn't account for either, you inevitably get situations where too many bandwidth hungry tasks land on the same rack, creating a hotspot. This is the fundamental problem: bandwidth agnostic scheduling in a bandwidth heterogeneous environment. This paper identifies that both Google's core infrastructure systems were designed to be network oblivious. Borg, Google's cluster scheduler, ignores network conditions when placing tasks. It optimizes for CPU, memory, and locality but not TOR utilization. Colossus, Google's distributed file system, ignores TOR capacity when deciding where to store the data chunks. This was actually a deliberate design choice. The network was supposed to be transparent, a reliable, and constrained source. That assumption held for a long time, but as workloads become more network intensive and heterogeneous, it began to break down. So this resulted in many intensive tasks ending up on the same rack, getting the network overloaded. And the paper also discusses 4 real production incidents which occurred at Google which are caused by hotspots. The first one is ad analysis slowdown, where a software rollout accidentally reduced TOR capacity by 50% on some switches because Borg was unaware it kept scheduling bandwidth heavy jobs on those racks, and it resulted in 2 to 3 times increase in the ad's batch job completion time. The second is a storage scheduling constraint bug. A team tried to reduce congestion by restricting scheduling away from a class of machines called D servers, but this had an unintended side effect. Workers got concentrated onto fewer racks, created persistent TOR hotspots, and this caused 1.5 times increase in read latencies. The third one is a YouTube watch history failure. A hotspot caused packet loss on a big table partition. This doubled big table replication latency, which led to users seeing stale or missing watch histories. And Colossus degraded spiral finally. When TOR congestion made some data chunks unreachable, Colossus tried to reconstruct them from other copies. This is called a degraded read, but that reconstruction generated even more traffic on the already congested TOR, making things worse. A classic positive feedback loop. These above incidents show that hotspots are not just theoretical concern; they have real cascading effects on production services. Congestion control algorithms like DCQCN or Swift paces traffic when queue builds up, but it can only spread traffic over time. It cannot create more bandwidth if the TOR uplink is persistently saturated. Pacing doesn't help. Packets just queue or drop. Load balancing like ECMP spreads flows across multiple paths through the network, but the key point is that all the paths from a rack share the same TOR. Multipathing helps with core network congestion. It doesn't help with the network bottleneck at the TOR itself. Traffic engineering optimizes routing across wider data center traffic, and it works well for the DCNI. But again, it cannot reroute traffic around single top of rack uplink. The top of rack is the first hop and there is only one per rack. None of the traditional tools address for the root cause. The only real fix is to move the work away from the hotspot TORs, which is a placement problem, not a traffic management problem. The paper also characterizes the hotspots. Top of rack hotspots occur at a rate roughly 10 times higher than the host to TOR link congestion. This confirms that the top of rack uplink, not the server downlink, is the binding bottleneck. Top of rack hotspots are also 2 times more frequent than DCNI link congestion, meaning the top of rack uplink is actually the most congested point in the network, not the core. 90% of hotspots occur on racks that have storage, either disk racks or mixed compute and storage racks. This strongly implicates storage traffic as the primary driver. The paper cites prior work noting that storage traffic accounts for about 75% of all data center traffic, and 40% of hotspots last between 1 to 12 hours, a substantial duration. Looking at the full distribution, 25% of them resolve in under 30 minutes, but 65% last more than an hour and 13% will persist for over a day. By rack type, 53% of hotspots are on mixed racks, 37% on pure disk racks, and 11% only on compute only racks. Hotspots are storage driven, they are persistent, and they require both proactive and reactive solutions. Short duration hotspots need fast reaction, while long duration ones can be addressed proactively. The paper discusses impact on storage operations. The pattern is consistent and striking. At low utilization, say under 50%, latency is basically flat. The network is not a bottleneck. But around 50 to 60%, latency spikes up rapidly. The relation is non-linear. It accelerates as utilization grows. At hotspot level utilization around 75%, latency has already increased to 2 to 4 times relative to the baseline, and it keeps getting worse at higher workloads. Writes are more sensitive than reads, which the authors attribute to write-back caching behavior. Writes involve more round-trip coordination, making them more exposed to network delay. The network bottleneck dominates even for operations that we typically think of as disk-bound. The disk isn't the limiting factor, the TOR is. The impact varies by workload. The paper studies several queries benchmarks. These are analytical workloads similar to TPCH and TPCDS. Network intensive operations like shuffle flush and materialize see the highest degradation, over 2 times latency inflation at high utilization. Compute heavy queries like TPCH Q02 are less affected because computation takes long enough to partially hide network delay. The practical implication is that network intensive workloads are most at risk from hotspots, and they are also often the ones that generate the most traffic, creating a compounding problem. The paper presents two solutions: UTP, which is utilization aware task placement, where we address compute task scheduling in Borg. It monitors real time TOR utilization and steers new tasks away from hotspot TORs, and migrates existing tasks of hotspot TORs reactively. And the second is CCP, which is capacity aware chunk placement, addresses data placement in Colossus algorithm. It classifies racks by their uplink capacity relative to the storage capacity and prefers placing new data chunks on well provisioned racks. Together, these two algorithms address the problem at both the layers, compute and storage. We'll look at UTP in more detail now. UTP has two modes: proactive and reactive. In the proactive flow, when a new task arrives for scheduling, Borg samples a set of random candidate servers across the cluster. This is the standard Borg approach. It then scores each candidate server on multiple dimensions, which can be CPU balance, data locality, and now we add an extra dimension called TOR utilization. The server with the best overall score is chosen. The design principle is that TOR utilization is a low priority tiebreaker. It never overrides critical objectives like CPU or memory balance. This keeps the system from making bad placement decisions for the sake of network performance. In the reactive mode, when a TOR utilization exceeds 75%, UTP identifies racks that are both latency tolerant and high bandwidth, meaning migrating them won't violate any SLOs. It then verifies the migration is within availability budgets and moves these tasks to racks with lower utilization. This dual approach, proactive avoidance plus reactive escape, turns out to be much more effective than either alone. Now we will discuss about CCP. CCP addresses the storage side of the problem. The insight is that link capacity per HDD varies about 2 times across the fleet. Some racks have plenty of uplink bandwidth capacity relative to their storage capacity. Others are under-provisioned. This happens naturally as disk densities improve faster than the network upgrade in some racks. CCP classifies each rack into one of three tiers based on the ratio of top of rack uplink capacity to storage capacity. High uplink racks exceed the provisioning guideline, and medium racks match the guideline, and low uplink racks fall below the guideline. CCP requires no live telemetry, just static capacity information about each rack, which is already known. It's encoding agnostic, meaning it works whether data is replicated or erasure coded, and it works in a multi-tenant environment. This is an advantage over prior work like Sinbad, which required real-time telemetry and was harder to deploy at scale. The evaluation is production scale and thorough. For data collection, switch telemetry was gathered at 5-minute granularity across the full fleet. RPC level latency breakdowns were captured using Google's Dapper tracing infrastructure. UTP was evaluated through a pilot cluster rollout followed by a fleet-wide deployment, measuring the fraction of hotspot TORs and P98 utilization before and after with statistical significance tested via students' t-test. CCP was evaluated in a 15-day pilot, measuring Colossus P95 read latency bucketed by cluster throughput level, allowing fair apples to apples comparison at the same load. Here we discuss about some results. UTP reduced the fraction of hotspot TORs by 90%. Monthly service incidents related to hotspots dropped by 70%, and P95 latency improved across workloads, with Shuffle Flush seeing a 13% reduction and Materialize seeing a 9% reduction. Comparing proactive plus reactive UTP to reactive only, 41% task 41% fewer task migrations were needed, and scheduling violations dropped by 74%. Proactive placement roughly halved the reactive workload by avoiding hotspots in the very first place. You have far fewer fires to put out. CCP results are even more dramatic. P95 network read latency dropped by 50 to 80%, and P95 total read latency improved by 30 to 60%. Here, total latency includes disk seek time. The fact that network layer improvements produce this large an effect on total latency again confirms that the network was the dominant bottleneck. These numbers are measured in production on Google infrastructure, not simulations. That makes them especially credible. Here we'll discuss about what makes the paper really strong. The results are from production deployment and not just a lab or simulation. 90% hotspot reduction at Google scale is a more credible result. Here the solution introduced was elegantly simple. The core idea of moving work toward bandwidth is intuitive, yet the implementation is pragmatic. CCP doesn't even need live telemetry. The measurement study is comprehensive. A month of fleet-wide data strongly motivates the problem. Both UTP and CCP are minimally invasive. They plug into existing systems as lightweight changes rather than requiring risky re-architecturing. The dual proactive plus reactive strategy proves to be genuinely better than either alone in nice system insight. We'll also discuss some limitations and weaknesses of the paper. The paper discusses no ML cluster coverage. The paper explicitly excludes GPU and ML clusters, which are among the most network intensive environments today and have very different traffic patterns. Like all reduce and collective communication, this is arguably the most important gap given current trends. Best effort, no SLO guarantees. UTP and CCP improve average behavior but cannot make hard guarantees as production systems move toward tighter SLOs. This matters. Limited generalizability. The solutions are tightly coupled to Borg and Colossus. Organizations using Kubernetes, HDFS, or other stacks would need significant re-implementation work. No multi-hotspot analysis. The paper studies individual hot TORs in isolation. It doesn't study about what happens when multiple TORs in the same aggregation block are simultaneously congested. These cascading scenarios aren't evaluated. CCP only affects new chunks. Existing chunks on low uplink racks stay there. The problem is mitigated over time as new data is placed better, but there is no mechanism for rebalancing existing chunks. Conclusions. The problem is real and persistent. Top of rack hotspots last for hours to weeks and degrade latency by 2 times or even more. Even for workloads you didn't expect to be network sensitive, traditional traffic management tools cannot fix this. Placement is the right lever. Simple hotspot aware placement like UTP for compute and CCP for storage achieves 90% hotspot reduction and 50 to 80% latency improvement in production. It's more effective than any traffic management approach. Proactive beats reactive. The combination of avoiding hotspots and escaping them deliver far better results than reactive migration alone. 2 times fewer migrations and 7 times fewer violations. The paper's closing message is worth quoting directly. Hotspot aware placement is crucial for achieving consistently good performance, more so than traditional traffic management. Thank you.